In this lecture, we are going to see some problems based on conjugate harmonic, and we are going to learn about how to construct an analytic function. So in this question, they have given that u equal to 1 by 2 log of x square plus y square is harmonic, and we have to find its conjugate harmonic. We know that f of z equal to u plus iv. So u is the real part and v is the imaginary part. U is harmonic by proving that you can able to find out what is the conjugate harmonic of U, which is V. Here we are having the function U as 1 by 2 log of x square plus y square. If you want to show that it is harmonic, you have to show it as satisfying the Laplace equation. Dou square U by dou x square plus dou square U by dou y square equal to 0. Now, to find out the second order partial derivative of u with respect to x and y, differentiate u with respect to x first. So that gives you differentiation of u with respect to x is differentiation of log is 1 by x square plus y square, and differentiating with respect to the variable x, x square will become 2x. So 2 gets cancelled. You are having x by x square plus y square. So you are having dou u by dou x is equal to x by x square plus y square. Likewise, dou u by dou y is differentiating u with respect to y partially. So you have seen here, you are getting y by x square plus y square. Now to find out the second order partial derivative of u with respect to x, again you have to use the division rule. That division rule is u by v formula. Okay, let us take this as u and this as v. So differentiation of v, you have to first write it as x square plus y square, that is v into differentiation of u is 1 minus u into differentiation of v with respect to x, it will give you 2x divided by v square, x square plus y square whole square. So by doing the simplification, you will get x square plus y square minus 2x square divided by x square plus y square whole square. Because of that only, we are having minus x square plus y square divided by x square plus y square whole square. So you can observe this. Here you are having y square minus x square divided by x square plus y square whole square. Similarly, you can find what is dou square u by dou y square. Then adding both, you are getting the answer as 0. Therefore, we observe that u is harmonic. Now we have to find out the conjugate harmonic of u, which is v. To find out conjugate harmonic of u, which is v, we are going to make use of the CR equation and total differentiation. We all know v is a function of x and y. V is a function of x and y. So we can write v in terms of dou v by dou x into dx plus dou v by dou y into dy. So we are not knowing what is Vx and Vy. Therefore, by making use of CR equation, dou V by dou X is minus dou U by dou Y, and dou V by dou Y is dou U by dou X. Substituting it, and you already found out what is the values of dou U by dou X and dou U by dou Y. Substituting here, you will get dV equal to minus y by x square plus y square into dx, minus y by x square plus y square into dx. Then plus dou u by dou x will give you x by x square plus y square into dy. But here you have to exclude x terms. So no, if you are excluding x terms, this term dou u by dou x will give you 0. That's why we are not considering the second part. So dv equal to minus y by x square plus y square into dx. Now integrating on both sides, you will get v is equal to minus y into minus y by x square plus y square into dx. So this is going to be minus y is a constant when you are doing the differentiation with respect to x. It will give you dx divided by x square plus y square. So which is nothing but 1 by a tan inverse of x by a. So what is a here? Constant is y. So 1 by y into tan inverse of, okay, tan inverse of, here we are doing the differentiation with respect to x by a. So you will get x by y. Therefore y gets cancelled. You are going to have minus, okay, minus sign tan inverse of x by y. Here you will get this term, okay, where c is a constant. So by doing the integration on both sides, you will get this answer. Now, next we are going to move on to the construction of analytic functions by Millie-Thomson method. Here, this analytic function methodology, by using Millie-Thomson method, we can straightly find out what is f of z. F of z, we know that it is u plus iv. So, when the real part is given, what is the formula for finding f of z? It is integral of ux of z comma 0 into dz minus I into integral of uy of z comma 0 into dz. When the imaginary part of the function is given, then we are having f of z equal to integral of vy of z comma 0 into dz plus I times integral of vx of z comma 0 into dz. So first you have to find out the partial derivative of u with respect to x and y, and then in the place of x you have to put z, and in the place of y you have to take 0. Then integrate with respect to z. So here, by making use of harmonic function, you can able to construct an analytic function. So how to find out? By making use of harmonic function. If the real part is given u of x comma y, we have to know what is v. To find v, we know what is here dv is equal to, we are having dou v by dou x into dx plus dou v by dou y into dy. But by making use of CR equation, you understood that uy equal to minus vx. So it is going to be uy into dx plus here vy equal to ux. So into dy. This is by CR equation. CR equation is Cauchy-Riemann equation. Ux equal to vy and uy equal to minus vx. So by making use of this formula, we are rewriting this, and then this is dv equal to. So integrating on both sides, okay, you will get the value of v. But one thing you have to note it down here, in the second term ux, you should not consider the terms which are depends upon x. So excluding the terms of x, you have to consider the y term alone and then do the integration with respect to y. That will give you the value of v. Okay. So here you can see this problem. If u of x comma y equal to x square plus y square, find v of x comma y and hence find f of z. So u of the function u equal to x square minus y square. To find v, we have to know what is ux and what is uy. Find the first order partial derivative dou u by dou x equal to 2x and dou u by dou y equal to minus 2y. Therefore, v equal to integral of minus uy into dx plus integral of ux In that you have to consider only terms which are involving y. So here in ux, no y term, therefore this will be considered as 0. So here integral minus of minus will give you plus 2y into dx. Therefore you are going to have 2xy. The second integral part is going to be 0 because it is not independent of x. Then, so v equal to 2xy. Now to construct an analytic function f of z, just we are going to write it as the value of u and the value of v. Then you can combine it. So here x square minus y square plus I times 2xy. Here minus y square you are having, that can also be written as I square into y square, because I square we know that it is equal to minus 1. So 2x into iy. So you can write it as x plus iy the whole square, which gives you x square plus I square y square plus 2x iy. So this gives you what? Z. Why we are writing like this? It is a function of z. Therefore, the right hand side also should be in terms of z. That's why we are doing the modification like this. So by f of z, we are getting it as z square. This formula also we can do it with the help of Millie-Thomson method. Here you are having the function u of x comma y equal to x square plus y square. Using Millie-Thomson method, how to find out f of z? Same example is given. So here it will be not plus, it will be minus. So ux equal to differentiation of u with respect to x gives you 2x, and differentiation of u with respect to y gives you minus 2y. Now this I can write it as what? Ux of x comma y. Likewise this I can write it as uy of x comma y. So in the place of x you are going to put z, and in the place of y you are going to put 0. Put x equal to z here, you will get 2z. Put y equal to 0, you will get 0. Then by using it in the formula, here the real part is given. Therefore the formula for construction of analytic function is f of z equal to integral of ux of z comma 0 into dz minus I times integral of uy of z comma 0 into dz. So ux of z comma 0 is 2z, uy is 0. Therefore integral of 2z into dz. Integral of 2z is what? Z square by 2. So 2 z square by 2. 2 gets cancelled. You are having z square. You are having f of z equal to z square. Hence, we have found out the same problem. We have constructed an analytic function with the help of conjugate harmonic function and with the help of Millie-Thomson method. Now, show this problem. Show that the function u of x comma y is sin x into cos hyperbolic y is harmonic. And find its harmonic conjugate v of x comma y, and the analytic function f of z equal to u plus iv. So u equal to sin x into cos hyperbolic y. Dou u by dou x is what? Cos x. Differentiation of sin x is cos x into cos hyperbolic y. You have to treat y as constant when you are differentiating with respect to x. Now differentiate u with respect to y. So treating x as constant, sin x, into differentiation of cos hyperbolic y. In previous lectures itself I have shown it. Cos hyperbolic x can be written as e power x plus e power minus x divided by 2. So differentiation of cos hyperbolic x is going to be e power x minus e power minus x divided by 2. This gives you sin hyperbolic x. So Differentiation of cos hyperbolic y is going to be sin hyperbolic y. Likewise, you have to find out the second order partial derivative of u x with respect to x again. Differentiation of cos x is minus sin x into cos hyperbolic y, and differentiation of uy with respect to y again will give you sin x into differentiation of sin hyperbolic y. So we know that sin hyperbolic y is e power x minus e power minus x divided by 2. So d by dx of sin hyperbolic, let it be x here, sin hyperbolic x is e power x, okay, minus of minus will give you plus e power minus x divided by 2. Therefore, this gives you cos hyperbolic x, which is cos hyperbolic x. Hence, differentiation of sin hyperbolic y gives you cos hyperbolic y. By adding these two, if we are adding these two, we are getting the answer as 0. Therefore, u is harmonic. So, if so, you can able to find out the conjugate harmonic of u, which is v. To find v, we are going to make use of the total derivative formula. So, v equal to integral of minus uy into dx plus integral of ux into dy. In this term ux, you should not consider any x terms. So ux, it is involving x terms, therefore we are going to take it as 0 here. Then you have to differentiate this uy with respect to x. So here we are getting integral of minus sin x into sin hyperbolic y into dx plus here x term evolving, so you are going to treat it as 0. Now integrating with respect to x, taking sin hyperbolic y as a constant outside, you will get integral of sin x. We know that integral of sin x is minus cos x. Therefore, v equal to cos x into sin hyperbolic y. Now you write it in terms of z. So f of z equal to u plus iv. Therefore, sin x cos hyperbolic y plus I cos x sin hyperbolic y. You want to express in terms of z. So we are writing this sin x into cos hyperbolic y is same as cos iy. Likewise, sin hyperbolic y is same as sin iy by y. Sin iy by I. These are all formulas. You can make a note of it. Cos hyperbolic y is cos iy. And sin iy is equal to I sin hyperbolic y. So by making use of these two formula, you can rewrite it like this. Now here cos of iy sin x plus cos x into sin iy. It is like cos a sin b formula. That is sin a cos b plus cos a sin b formula. It gives you sin of a plus b. In the place of a, you are having x. In the place of b, you are having iy. So sin of x plus iy, which gives you sin z. Hence, f of z equal to sin z, and v also we have found out. So this is the methodology of finding the analytic function by making use of conjugate harmonic methodology.